Hey all, welcome back. Today's video is about autocorrelation and autoregressive models. Let's build up to autoregressive models by starting with autocorrelation. Autocorrelation is a measure of how a time series relates to its own past values. Consider this time series plot here, showing 100 data points over time. In the table below, we see the first 10 values from the time series. Our goal is to see if there's any pattern between the values and their previous or lagged values. Looking at the last row in the table, we create it by shifting the values from the row above it forward one step. For example, take the value at time 1 in yt and shift it forward. It becomes the value for yt minus 1 at time 2. Similarly, the value at time 2 shifts over to become the lagged value for time 3. We repeat this process for every single time step. It's the exact same numbers, just delayed by one time step. Now, let's get rid of t and just look at the relationship between y sub t and its past self. We can plot these pairs one by one. Here's the point for t equals 2, appearing at an x-axis value of 0.50 and a y-axis value of 0.37. Next, we have the point for t equals 3, appearing at 0.37, 0.43. For t equals 4, we have the point 0.43, 0.64. If we continue this for all t, we reveal a clear linear pattern between y sub t minus 1 and y sub t. It's not random after all. This relationship is known as autocorrelation. It is a measure of how much a time series is linearly correlated with a lagged version of itself. Let's introduce some formulas to understand how we represent autocorrelation in time series data. Recall that the Pearson correlation statistic, R, measures the linear relationship between two separate variables, x and y. In this formula, t minus 1 represents the number of observations in our dataset, adjusted for the degrees of freedom. The terms Sx and Sy are the standard deviations, which normalize the calculation from covariance to correlation. And x bar and y bar represent the mean values of the respective variables. Now, what happens if we only have a single time series, y, and want to calculate the correlation between yt and its previous value, yt minus 1? We can replace x in the Pearson correlation formula with y sub t minus 1, adjust the summation to start at t equals 2, since we don't have a previous value for the first observation, perform some simplification, and get us the formula for the lag 1 autocorrelation, represented by r sub 1. There are some assumptions we need to make to get to this formula, but they're beyond the scope of the syllabus material. The general takeaway is that r sub 1 is the lag 1 autocorrelation between y sub t minus 1 and y sub t. We can generalize this concept to any arbitrary lag k by replacing y sub t minus 1 with y sub t minus k. This gives us the general formula for the lag k autocorrelation statistic. So how do we interpret these statistics visually? First, a positive autocorrelation indicates persistence. If the series has a high value now, it is likely to remain high in the immediate future. Second, negative autocorrelation suggests mean reversion. If the value is high at time t, it is likely to be low at time t plus k, resulting in a zigzag pattern. Lastly, zero autocorrelation implies there is no linear relationship over time. The series behaves essentially like random white noise. Let's go through an example. Here is our problem statement. We have a time series, yt, with 7 sequential observations. Our goal is to calculate the lag 2 autocorrelation. To solve this, we'll use the standard formula for autocorrelation at lag k. Since we are looking for lag 2, we set k to 2. We also have 7 total observations, so capital T is 7. First, we need to calculate the mean. We take the sum of all the observations and divide by the number of observations, which comes out to 9. We can also simply observe that the mean is 9 because the data is evenly spaced, with 9 being the middle value. Next, since we need all the deviations from y equals 1 to 7, we'll calculate all of them at once and plug in the appropriate parts into the numerator and denominator later. Calculating this out, this gives us our deviations: -6, -4, -2, 0, 2, 4, and 6. We now use the deviations and plug them into the formula for the numerator. We pair up the first deviation with the third, the second with the fourth, and so on for t equals 3 to 7. Multiplying these pairs out gives us 12, 0, -4, 0, and 12. Summing those products together, we get a total numerator value of 20. For the denominator, we square each deviation and sum them up, adding up 36, 16, 4, and so on, resulting in a denominator value of 112. Bringing it all together, we divide our numerator, 20, by our denominator, 112, resulting in a lag-2 autocorrelation of 0.179. Now that we've covered autocorrelation, let's introduce the autoregressive model of order 1, or AR1 model. For t greater than 1, we represent the AR1 model with this equation, where the value at time t depends on an intercept, a multiple of the previous value, and an error term. The 1 in AR1 refers to the lag. An AR2 model would include a sum of the first and second lags. An AR3 model would include a sum of the first 3 lags, and so on. The syllabus only requires specific knowledge of AR1 models, so we won't cover higher order models in detail in this video. Here, similar to linear regression, beta 0 is a constant and beta 1 is the slope parameter. We can estimate beta 0 and beta 1 using conditional least squares estimates. Conditional least squares is similar to ordinary least squares, but we use the lagged value of y as the explanatory variable. It is an approximation because the first value has no lag, so it is not used in the estimation. This causes slight differences between the conditional least squares estimate and the ordinary least squares estimate, which diminishes as the series length increases. Using conditional least squares, we can approximate beta 1 as the lag 1 autocorrelation statistic from earlier in the video, and beta 0 as the sample mean of y times 1 minus beta hat 1. We'll go through an example later in the video. Note the similarity to the formulas for beta hat 1 and beta hat 0 from ordinary least squares. In conditional least squares, we use the lagged value of y as the explanatory variable x, so the sample standard deviations of x and y from ordinary least squares effectively cancel each other out in the slope estimate. In the intercept estimate, the sample mean of x is approximately equal to the sample mean of y, which gets you the formula in the conditional least squares estimates. The last term, epsilon t, is a white noise process, where the covariance between epsilon t plus k and yt is 0 for any lag k greater than 0. Let's look at how changing these parameters affects the AR1 model. We will examine 3 distinct cases based on the value of beta 1. In the first case, when beta 1 is strictly between -1 and 1, the series tends to revert to its mean. It is stationary. If beta 1 is exactly 1, the formula simplifies to the previous term plus a white noise process with drift. We know from the previous video that this is the familiar form for a random walk model. A random walk is non-stationary and wanders off. If beta 1 is 0, the model simplifies to white noise plus a constant. There is no memory of previous values. This is a special case of the first condition, since a white noise process is stationary by definition. Alright, next up, model selection, or how to figure out if an autoregressive model is actually appropriate for your data. Okay, first, let's get organized. When an autoregressive model is stationary, we can use a control chart to check for stability. But here's the thing. Stability doesn't necessarily mean that the model is autoregressive. So alternatively, we can also detect AR1 models using a scatter plot of current versus past values. Notice how the points form a clear linear pattern. If we spot this pattern, we can be confident that the model is autoregressive. For an AR1 model, The autocorrelation between points k time units apart is defined as beta 1 to the k power. Since a correlation is bounded by 1 and -1, the exponential implies that the autocorrelations decay geometrically as the lag increases, since raising the correlation to a power makes it smaller the higher k is. Basically, the strength of the relationship diminishes as the time gap widens. For white noise, where beta 1 is 0, the correlation is just 0 for all lags. So, to identify a suitable model, one can match observed autocorrelations, R sub k, with these theoretical expectations. A useful application is identifying white noise. If the time series is white noise, R sub k should be close to 0 for all lags. If we observe geometric decay in the sample autocorrelations, then the model might follow an AR1 process. Let's say our theoretical lag1 correlation is 0.814. Then an AR1 process predicts lag2 will be 0.814 squared, which is 0.66. Lag3 would be cubed, resulting in 0.54, and so on. If our observed values in the bottom row closely match the theoretical expectations, which they do here, then we can be confident that the model follows an AR1 process. Another way to check if the sample autocorrelation is significant is through hypothesis testing. For a white noise process, the standard error of the sample autocorrelation at lag k is given by the formula shown here. Notice that it is purely a function of the number of observations in the time series. Our null hypothesis is that there is no autocorrelation at lag k. The alternative is that autocorrelation exists. To test this at a 5% significance level, we look at a critical value, which is approximately 2 times the standard error. If the absolute value of R sub k is greater than this critical threshold, we reject the null hypothesis. The correlation is significant. If it is less than or equal to the threshold, we fail to reject the null hypothesis. If this holds for all lags, the series is likely white noise. Let's briefly cover some estimation formulas for an AR1 model so we can use them in an upcoming example. The residuals of an AR1 model are defined as the difference between the observed value at time t and the predicted value based on the previous time step. Analyzing the residuals can reveal ways to improve the model specification. Patterns in the residuals may suggest modifications to the model. Now, we use these residuals directly to calculate the mean squared error. The mean squared error is estimated using this formula. The denominator is t minus 3 to account for the fact that the first residual is not used in the calculation, and we lose 2 degrees of freedom for the estimated slope and intercept parameters. Be careful not to forget the t minus 3 in the denominator when applying this formula on the exam. Let's dive into a numerical example. This is from the Society of Actuaries Sample Questions. The setup is simple once you know which formulas to use, but the arithmetic gets pretty messy in a test environment. This is a good example because it lets us apply several formulas we've learned so far. Here is our data. We have time points 1 through 6 and the corresponding y values ranging from 31 to 51. We are asked to calculate the mean squared error using conditional least squares. Before we start crunching numbers, let's think about which formulas we need to use. We'll need the MSE, which is given by this formula. Note the denominator is t minus 3. We lose the first observation because of the lag, which is also why the summation starts at t equals 2 instead of t equals 1. Then, similar to ordinary least squares, we lose 2 more degrees of freedom for the estimated intercept and slope parameters. To calculate the MSE, we'll need the residuals. To calculate the residuals, we'll need to estimate beta 1 and beta 0. So to get there, we estimate beta 1 using the sample autocorrelation, and beta 0 using the sample mean times 1 minus the sample autocorrelation. We then calculate the residuals by taking the observed value and subtracting the predicted value. Okay, let's go through the calculations step by step. Time to whip out the calculator. First, we calculate the mean. After summing the values and dividing by the number of observations, we get 40. Next, we calculate the autocorrelation coefficient. This is one of those awesome formulas where we get to use like the entire column of operators on our calculator. Yay. So using our trusty calculator, beep beep bop, carry the 2, and boom, 0.4466. Next, we plug the mean and slope estimate to the beta 0 hat formula, resulting in beta 0 hat being 22.136. Now for the residuals. We plug in the intercept and slope estimates to the residual formula, resulting in the following equation. We then need to calculate the residuals from time 2 to 6. For t equals 2, we take 35 minus our prediction based on 31. That gives us negative 0.98. For t equals 3, we use 37 and the previous value of 35. That's negative 0.77. We continue this process for all data points to get the rest of the residuals. Almost done. First, we find the average of those residuals we just calculated. It's about 2.78. Now we sum the squared differences from the mean and divide by 3. Crunch those numbers and voila! The mean squared error is approximately 22. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.